of this video is to review ideas from chapters 4 and 5. Now it's easy for me to look in the chapter, identify learning objectives, share representative questions, but how are you going to use this information? One way is to make a checklist. As I go through the range of topics, ideas, and skills, make sure these are ones that you are aware of that you're going to need to master for the test. You can use it metacognitively. For the different topics, think about your own understanding. Try to authentically test yourself so you can evaluate that and address weaknesses. You want to transform this material in some way and make it so it's useful to you. Don't just look and say, oh yeah, there was information within a video. Try to take it and make it so it's useful for you. Transform it, put it into your own words, make your own document. And finally, consider what you can practice and overlearn. There are particular skills, especially ones that take longer to execute, that you really want to master so you can quickly recognize a problem and execute it on a test. Looking at Chapter 4, we began by looking at general properties of aqueous solutions. We classified them in different ways: non-electrolyte, weak electrolyte, and strong electrolyte. We saw examples that were non-electrolytes, in which we had molecules staying together when they dissolved in water, strong electrolytes that dissociated, the manner in which they dissociated, whether we had polyatomic ions or the resulting cations and anions present. We saw a class of ionic compounds that were strong electrolytes, were the strong bases. And we also had a molecular example as a strong electrolyte, and those were our strong acids. Weak electrolytes, that's where we placed our weak bases and weak acids. A lot of information on this slide. We began with chapter 4, introducing the idea, and then once we learned more, we added a lot to it. So how will this show up on the test? Here are two different examples. On the left, we see either formulas listed or names listed, and it's asking, well, what's in the beaker when something dissolves? And on the right-hand side, particle level representations. For these or for any, if you're unsure about the question, show your work, ask about it. Let's compare ideas. When we had oxidation reduction reactions, we had different skills there. We need to be able to determine the oxidation number in any compound. With that information, identify what is being reduced and what is being oxidized in a reaction. Remember those terms for what is being reduced and what is being oxidized. That's referring to the reactants. Reactants are oxidized when they lose electrons, and they are reduced when they gain electrons based on the change in their oxidation number. Here's an example where you have to identify which reactions are redox reactions, and if they're not, are they precipitation or neutralization? I would add to that, if they're precipitation or neutralization, try to write a net ionic equation and identify the spectator ions. Related to this was using the activity series. I share a description on the left-hand side from the textbook for how to use it. I'll add to that, well, what do you observe when you have an experiment like this? If you take a piece of copper metal and you put it in a solution that includes silver ions, what happens? Well, I'd say that the copper begins to dissolve and the silver solid begins to form on the surface of the copper metal. I'm trying to connect observations with the data that we have with the activity series, which will be provided. Here's an end of chapter question. This is an example where we have different scenarios listed. What would happen if nickel metal is added to a solution of copper nitrate? I see the nickel solid is above the ion in terms of ease of oxidation, so I think the nickel solid will dissolve and give me nickel 2+ as it becomes oxidized. The copper 2+ is reduced as copper solid is formed. There's a question involving hydrochloric acid because H+ is listed on the activity series, and one involving hydrogen gas, which is H2, because H2 is listed on the series. Here's another end of chapter question, looking at it a little bit differently. This one provides data and asks you to prepare an activity series. So how would you go about that? Well, if we look at the examples at the bottom, those observations, those are redox reactions. I could use that to place Br2 and I2 relative to each other, because I see for that first one, that redox reaction takes place. This is telling me that the bromine is being oxidized and the iodide is being reduced, so I'd place it that way within the series. So we want to be able to use the provided data with an activity series and also know what it means, because here's a question where we had to go in a different direction. When it comes to precipitation reactions, we want to be able to use provided solubility data. Typically, it's predicting whether a precipitate forms. If it does, write a net ionic equation and identify spectator ions. That might be where we have formulas given. It might be when we have the names of the compounds given. It might be when things are given in combination. Give this one a try. Read the question there. If these three solutions are mixed together, what solids are going to precipitate? I'd first recognize, in each case, what is it putting in the beaker? When the lead acetate dissolves, what ions are present? How about the sodium sulfide or the calcium chloride? So I'd say these are the different things that are being placed within the beaker when those particular ionic compounds dissolve. And I see that I could have both lead chloride and lead sulfide being combinations that then precipitate. Acid-base neutralization reactions. We need to be able to classify substances as strong or weak acids or bases based on their chemical formulas or structures. So we need a plan for that. Remember our plan? We're going to memorize the strong acids, and any other acid beyond that must be a weak acid. Our strong bases, those were our ionic compounds with the hydroxide and our alkali or alkaline earth, sodium hydroxide, potassium hydroxide, stuff like that. As far as our weak bases, classic example was ammonia, NH3, and our other ones that we looked at were other nitrogen-containing compounds. We also want to be able to write equations that are describing neutralization with an acid and a base. Give this one a try. I think within this one you should be able to identify all of these as being strong, weak, or non-electrolyte, and also if it's an acid, base, or neither. In this case, we're looking for something that is acidic and weakly conducting. I see two different acids listed, nitric acid and phosphoric acid. Nitric acid is a strong acid. It is going to be strongly conducting. It says that, therefore, it's not correct. It says in this case, we're looking for a solution that's acidic but is weakly conducting compared to sodium chloride. That's going to be the weak acid. That's going to be phosphoric acid. In terms of being able to determine a net ionic equation, give this one a try. My plan is I will write dissociated all of the aqueous strong electrolytes. I'll cancel out the ones that are appearing on both sides of the equation. Those are my spectator ions, and I'm left with the net ionic equation. Remember our plan when it comes to writing a net ionic equation? We're going to first write a balanced equation. Next, we will dissociate all of the strong electrolytes that are aqueous. And then finally, we'll cancel out the terms that we have and reduce it down to the net ionic equation. That's what's taking place here. Concentration of solutions. Different ideas in this. We saw that molarity was a unit for concentration. We need to be able to convert between molarity, moles, and volume and perform dilutions. Molarity is the moles of solute per liter of solution. Here was an example where we want to first recognize as a strong electrolyte, how does it dissociate? How many moles of the different ions do we have in solution? And now we can express that to talk about the molarity. In this case, it was looking for the sodium ions. Key step, recognizing how does it dissociate in the first place. That's what was being applied here. We saw that in each of these cases, they're strong electrolytes. But when we look to see then how they dissociate, we need to account for whether we had 1 potassium per formula unit, 2, or 3. That's for part A, when we're looking for which of these would give us the highest concentration of potassium ion in the solutions. In part B, we're looking for the greatest number of moles. Now, more than just the concentration is given. We have both the volume and the concentration, and we're going to combine those. With solutions, we can combine the molarity and the number of liters to get to the number of moles. Molarity is moles per liter. So moles per liter times number of liters gets us to number of moles. This is a key idea that we need to have when we're doing solution stoichiometry. So in this one, we know in each case how the solute dissociates. If we know how many moles we start with, then we can know how many moles we're going to finish with. How do we figure out how many moles we start with? We're going to use that solution information and then account for how it dissociates. There's my answer for how many moles of potassium ions I get in one case and in the second. The idea of using solution information, we also change the concentration by doing dilutions. That's where we have the equation M1V1 equals M2V2. And so in this one, we see how we are transferring the solution using a pipette. We're putting it into a volumetric flask. We are now filling it up to the line with water, and we see what the new concentration would be. Here's examples for you to try on this subject. Where we're calculating the concentration, we're doing dilutions. Last idea was solution stoichiometry. Here's an example of a titration. We're interested in what volume of the strong acids needed to neutralize sodium hydroxide. So we got to start with a balanced equation. We've got solution information for the base. And when I look at the balanced equation, the acid and the base are reacting 1 to 1. I can use the solution information to figure out how many moles of the base were present. I can then use the solution information. I've got 2 out of 3. What's missing would be the volume for the acid, so I could solve for the acid term. Here's another one. I see an acid and a base, but I got to start with a balanced equation. This one's not a 1-to-1 stoichiometry. There's 2 HCl's for every 1 calcium hydroxide. Crucial step, start with a balanced equation. Now if I look in this case, I have solution information for the hydrochloric acid. I have concentration and volume. I can get to the number of moles of the HCl. And then I have to ask, well, how many moles of the calcium hydroxide do I need? That's where I use the coefficients. There's 2 HCl for every 1 calcium hydroxide. So the number of moles is listed there. I'm going to make that big because I know that is the key thing that we need to account for. The number of moles of the base that would be used. And in this case, it's not asking for the amount of base in terms of the solution, it's asking for grams. So I'm going to convert that using the molar mass for the calcium hydroxide. So look within the different topics here that we have within Chapter 4. Which of these are multi-step skills that is going to be beneficial to overlearn? As I look at that, using the activity series, we want to overlearn that and make sure we're very proficient at that. A plan for writing net ionic equations, we want to overlearn that. Being able to do dilutions, and especially aspects of the solution stoichiometry, these are all skills that we don't want to be clever during the exam. We just want to have a plan that will always work. Practice a plan and make sure that it always works. Moving on to Chapter 5, we begin by looking at aspects of chemical energy and the first law of thermodynamics. We saw descriptions of the potential energy when we were interested in particles that were being attracted to each other because they had opposite charges, or ones that would be repelled from each other because they had the same charges. Most of the time we're interested in the attractions, how we can have the particles of matter coming together and moving to a lower, a more negative potential energy. Let's look at this a few different ways. So when we're thinking about energy, the internal energy, that's the sum of all the kinetic energy and all the potential energy for all of the particles that we have present. We saw how we could change that involving either Q or W. That was involving heat. Q was positive, corresponding to an endothermic process where heat was going into the system. When Q is negative, it's exothermic. Heat is going from the system into the surroundings. We also had the designations for work. Key thing we're looking at there is to consider, is there a change in the volume? When the volume of the system is decreasing, when it's getting squished smaller, work is going into the system. That was work with a positive sign. When the system's volume is getting larger, the work was negative. We looked at different scenarios. Here's an example. where we're seeing a reaction take place, and we see how the system is pushing against this piston and expanding it. PV work is being done. I would say the work in this case is negative. The system is doing work on the surroundings. This idea of charges attracting each other, connecting it to potential energy, here's a question that we explored. I would say the choice there that has the positive potential energy, well, I'm looking for the one where both of the charges are the same sign. When I'm thinking which one has the most negative, the smallest value, that's where we had opposite signs and they were close to each other. And they were also of a larger magnitude than what I see here for choice C. One closest to 0 is when they were furthest apart from each other. Here's an end of chapter 1 that's on the same topic. Now this one's on the same topic where it's looking at these two oppositely charged spheres. It also brings up the idea of internal energy, so I'm thinking about terms involving heat and work as well. So if I look at this, it begins at position 1, and then it's being pulled apart to this larger distance. So was there a change in the potential energy? I think there was. I think the potential energy increased as these particles that were attracted to each other were brought to a greater distance. I think the potential energy went up. It went closer to 0 given my definition of having a reference of a large separation. Did this have any effect on the internal energy? Well, if the internal energy is both the kinetic energy and the potential energy, yeah, I think that the internal energy went up because the potential energy has gone up. Now, did this involve anything with Q or W? Well, it had to involve one of them because these are the terms that I can use to change the internal energy. I don't think I'm doing any heating here, but I am doing work in order to pull them further apart. I think that's what was taking place. Here's a question involving internal energy and connecting it to heat and work. Give this one a try. In this first scenario, I'm reading that the balloon is being cooled down. So I think heat is leaving the balloon. If that's my system, that would be exothermic. And that I see that upon this, the balloon is shrinking in size. Its volume is going down. So work is being done on the system. I'm defining the balloon here as the system. I converted both of those to joules, and I see what the overall change then is in terms of the internal energy. Exothermic process, because heat is going from the system into the surroundings. Here would be the second example. So it says the bar is being heated. So I would call that an endothermic process. I would say, in this case, it says that the volume is staying constant, no change there. So I think the internal energy is going up because the bar is being heated, but no work is being done. Here's another scenario. Take a second, read through this one. So again, I'm thinking about the internal energy, heat, and work. In scenario A, energy is being added, 100 joules is being added. I think that the temperature of the system is going up, and I think that the piston is being moved outward. I think heat is going into the system, and the system is now doing work on the surroundings. The second example, same setup, but it was confined so there could be no volume change. So I think heat energy is being added, the temperature of the system increases. This is again an endothermic process, but there is no volume change in this case. So I think in that second one, there's a greater temperature increase because for the same amount of energy, there was not any work being done. The work, therefore, was not somehow canceling out an aspect of the energy that was being added. So I think this leads to a greater temperature increase, a greater change in internal energy. Looking at enthalpy and enthalpies of reactions, we did qualitative rankings. These are not ones where we're referring to any data table. We're just thinking about what enthalpy corresponds to. And we had examples where we connected it with stoichiometry. When we're connecting it with stoichiometry, we have to really be careful and look for what are the coefficients that we have. And also, as I look within this first one, when we're thinking about different mole amounts, those could be connected back to solution information. We said that if we have molarity and volume, we can use that to get number of moles. So that's another way that solution stoichiometry in number of moles can fit with a reaction where we have a delta H value. When we're looking at Hess's law, these are easy to recognize. And as I look at this, like other calculations I'd expect on your test, this would be an open response format. There's no reason for this to be multiple choice. This fits very well of calculate a value and report it. When we're doing calorimetry, we saw several examples. I know you also saw examples pertaining to lab. My strategy here for any of these, I try to make it so I've got a plan that I can reproduce. I want to think about whether it's an exothermic or endothermic reaction, how much heat was involved, and how do I report the enthalpy change. Exothermic or endothermic, I'm looking to the thermometer for that. That will tell me if it's endothermic or exothermic. Exothermic means the temperature is going to increase like this explosion. If the opposite occurs, if the temperature decreases, it must be an endothermic process. Look at the thermometer first. How much heat was involved? Well, in this case, we have a specific heat value given, using that for water. The total amount of solution that changes, I have its mass value, and when I say total amount, I'm making an aqueous solution, and I need that entire mass in my calculation, and I've got the temperature change, so I can figure out how many joules or kilojoules were involved. How to report it? It says calculate the enthalpy change in kilojoules per mole of the ammonium nitrate. So I need to figure out how many moles of ammonium nitrate did I use. I know how many grams. Let's figure out how many moles using the molar mass, and now we can report it in kilojoules per mole. So with that very last step, I make sure that I'm accounting for the sign correctly. Endothermic, it's going to have a positive sign. Here's some examples of using calorimetry data to see if you have a plan that works. Enthalpy of formation, we want to be able to both identify and use that information. When I say identify, I think you should be able to write the standard enthalpy of formation reaction for anything. I mean, that seems like a bold claim, but I think anything. You know what the plan is. You're going to make 1 mole of that particular substance as the reactant. Fractional coefficients are okay, and you're going to have those elements as they appear in their standard state. With that information, I think you can write it for anything. How do you use it? Well, standard enthalpy of formation data would be provided. That's not something that you memorize. You set it up where you're interested in the values for the products minus the reactants. Make sure you account for the coefficients properly, and be careful with any signs, because some of the values might be positive and some of the values might be negative. Last idea was using bond enthalpies. In that case, we typically have one where we see the different molecules that are involved. We're seeing the different molecules because we need to then look at the specific bond enthalpy values and the corresponding energies. We can add up all of the values that it takes for breaking the bonds and subtract from that all of the values that we have when we're forming the bonds. Bond breaking is an endothermic process. Bond forming is an exothermic process. That can be used to get the overall enthalpy change. We want to be able to do calculations involving this and also have a conceptual understanding. Conceptual understanding, once again, bond breaking is always an endothermic process and bond forming is always exothermic. So as I look at this set right here, what ideas should you overlearn within Chapter 5? I think it's definitely beneficial to overlearn aspects of Hess's law and calorimetry. You want to make sure that you have a plan that you can quickly implement for both of those. Both of those have multiple steps involved. You don't want to try to figure it out. Make sure you have a plan that is practiced and works for both of those categories. As a second tier, I would say applying stoichiometry for an enthalpy of a reaction, using enthalpy of formation data or bond enthalpy data. I say second tier because I think those are all ones that are more easily accomplished. It's going to be great to have a plan that you know always works, but that plan is not quite as complex. So to finish up here, when I say it's easy for me to describe learning objectives and share representative questions, that's what I've tried to do here. But now it's up to you. Okay? Make sure you have a good checklist and you know the full range of topics, ideas, and skills that I discussed here. If you have weaknesses, now's the time to address them. Make sure you've taken this information somehow off of this video and you've transformed it, and it's a way that you can now remember the information and you find it useful. And be sure to practice and overlearn skills that we discussed. So those questions, even though they're more complex, they become easy for you to recognize and execute on the test.